Hello DC candidates, welcome back to School for All. As I said in my previous video, School for All will follow you till the end of your DC examination. Okay. And also, if you are seeing me talking about prepare concours, it's because majority of our staff is holding what? A prepare concours called Confidence Corporation. Confidence Corporation is a reference anglophone group for career orientation and prepare concours. So if you want to know more information about the date at which the prepare is launched or about the opportunity that you have after your GCE, feel free to contact me. My number is in the description. Let's start today's lesson. Okay. Now, I wonder we should focus today on paper 1. But I have something to say about paper 1. You should know that paper 1 is how many questions? 50 MCQs. Okay. Now, you should know that the setting of any exam is such a way that an average student is okay. An average or a normal student should pass. It means that what? An average student or a normal student should have at least 25 to 35 on 50. Let's say a student that is studying normally is okay. Now, as like there are 15 to 20, let's say 15 to 10 questions, sometimes 20 questions. That's a challenging question to make a difference. To make a difference between those A grade students, B grade, and C grade students. So there are 15 to 20 challenging questions, or to 10 challenging questions for them. So today I wonder we should target on those challenging questions, and I hope that it will help you in your upcoming paper 1 examination. So we are starting is question 42. Figure 2.1 shows two sinusoidal waves of the same frequency and amplitude. It's okay. Amplitude, and the amplitude is given as 0.05 meters. Travels along the same string in the same direction. Okay. So if the phase difference between them is pi all over 3, so we are having a phase difference between the waves is pi all over 3, which of the following statement is true? Or which of the following statement is correct? Okay, the first statement is the resultant amplitude is 0.0866. Okay, we all know that what? The resultant amplitude of the two waves, resultant amplitude, is given as 2 times the amplitude cos phase difference divided by 2. So that's how we calculate the resultant amplitude when you are giving what? 2 waves. It's okay. Superposition of 2 waves. This is how we calculate the resultant amplitude. Now, so I will have 2 into 0.05 meters cos in bracket pi divided by 2 will be pi all over 6, which is 30. So I'll have 2 into 0.05 times cos 60. And pardon, it's cos 30, pardon. So it's the same as cos 30 degree. Okay, so let us do the numerical application. Okay, while doing the numerical application, we obtain 0.0866 meters, making the first statement to be correct. Okay, so we're making the first statement of the equation to be correct. Now let us move to the second statement. Now the second statement of the equation is constructive interference occurs if the phase difference is pi. Now what you should know here is that constructive interference occurs only when the phi, which is what? The phase difference, can be written as what? Can be written as even number of pi. That's what you should know. Even number of pi. Example, 2 pi, 4 pi, and all that. So constructive interference occurs only when the phase difference can be written as what? Even number of pi, making statement 2 to be wrong. Now let us go to statement 3. Now statement 3 is the destructive interference occurs when phi is Destructive interference occurs when phi takes the value pi all over 3. Okay, from the definition, you also know that what destructive interference occurs when phi, the phase difference, is written as what? Is written as odd numbers. Are we together? Is written as odd. Is written as odd multiple. Pardon. Odd multiple of pi. So making the second one also to be wrong. So the only statement which is correct here is what? Statement 1. Constructive interference occurs when the phase difference is written as what? Even multiple of pi. Destructive odd multiple of pi. So that is it. Making the correct answer to be 1. From there, you choose your correct proposal. Now let us move to the next question. The next question we are having, figure 10 shows how an opposite student connects a bulb across a light-dependent resistor. So we are having a circuit like this. Let me draw it fast. Then I connect a bulb here. Okay, now the first statement, so we are having this circuit. Now the first statement is, without resistance R, the bulb will shine under bright light. The first thing here you should know is that what is the meaning of LDR? LDR means light dependent resistor. Are we together? And for a light dependent resistor, we know that what? For a light dependent resistor, so when it is exposed to light, the resistance, what? The resistance reduces. Is okay. And when it is not exposed to light, the resistance of the LDR increases. Is okay. So the resistance reduces here when it is exposed to light. Here the resistance of the LDR increases when it is not exposed to light. So that is why you should first of all know. Now the first statement is saying that without resistor R, the bulb will shine under bright light. Let us interpret the question, the statement. This is how current is flowing. Is okay. So current will reach here like this. Now if I remove this resistor R, yeah, if I remove it, I will have a branch here like this. I'll have. Now look up. When light shine, when the LDR is exposed to light, what happens? When the LDR is exposed to light, the resistance of the LDR reduces. It means that what? The resistance of LDR reduces means that current will flow. It means that we leave current to flow through him. So it will resist until we can replace the LDR as a wire like this, because it will leave current to flow. Is okay. Therefore, current will flow here and will not prefer to flow here. No. Because here the resistance is too low that we can replace it by a wire. It means that there's nothing here that opposes the flow of current. So current will prefer to flow here than preferring to flow in here. Therefore, short-circuitating this thing. It means that no current will flow here, so the bulb will not shine. I hope you understand what I'm saying. Because when the resistance of the LDR decreases, it means that what? Current will, there's no opposition of flow of current there, therefore current will go and flow there. I can replace the LDR by what? By a wire. So current will prefer to flow there than to flow where there is a bulb, because the bulb is having a high resistance. Therefore, no current will flow here, therefore short-circuitating this bulb. Therefore, the bulb will not shine, making statement 1 to be wrong. Okay, statement 2 now. Statement 2. Under low light intensity, the potential difference across the LDR is low. Under low light intensity, let us see. Low light intensity means that what? When it is not exposed to light, the resistance increases. Let us come back here. When the resistance of the LDR increases, it means that what? No current will flow. I can replace it by an open circuit. Are you understanding? So I will have something like this. To make sure that no current is flowing, I will replace by an open circuit. It means that current will rather flow like this. You rather pass here because here the resistance is too high. No current will flow here, therefore it's an open circuit. It's okay. Therefore this is our battery. So something like that is okay. It means that what? It means that current will prefer to flow here. Therefore, if I want to measure now the potential difference across the LDR, remember that the LDR is here. So this is our LDR. Is okay. Is parallel to this one. Is parallel to it means that if current is flowing here, it means that the voltage here is I times the resistance of the bulb. And if it is parallel to this one, therefore they should have the same voltage. Are we together? Therefore, if a rich amount of current is flowing here with the high resistance of the bulb, therefore the voltage will be high. Therefore, the voltage of the LDR will also be high. Therefore, the PD across the LDR when light is shining, when low light, when the intensity of light is low, the PD across the LDR will be high. So PD across the LDR is high. I hope I understand, because the PD across the LDR is coming from who? The PD of the bulb. Since the PD of the bulb is high because all the current is flowing here, because here the current is not flowing because the resistance of the LDR is too high, all the current will flow here. Therefore, since they're in parallel, the PD is higher, making the PD to be higher, making the PD of the LDR to be high, making the statement to be correct. Let me verify. Under low light intensity, the potential difference across the LDR is low, making the statement to be wrong, because the potential difference across the LDR is rather high. Now, statement 3. The bulb shines when the light intensity on the LDR is low. Very correct. The bulb will shine when the light falling on the LDR is low. Look up. When the light falling on the LDR is low, let me come back here. When the light falling on the LDR is low, it means that what? Let us choose. The resistance of the LDR is high. Is okay. It means that the resistance of the LDR is high. We are still under this case. When the resistance of the LDR is high, it means that no current will flow through the LDR. I can replace the LDR by what? An open circuit, making all the current coming here to flow through the bulb. Therefore, the bulb will shine, making statement 3 to be very correct. Okay. Without wasting time, let us move to the next question. The next question is talking about RLC circuit. So I'm having a circuit like this. Let me draw it fast. So this is my RLC circuit. Okay. So if you can understanding what is going on here, please, I invite you to go and watch my previous video under RLC circuit. I really explain all the concept under that. Now, the first statement is which of the following is or are correct? 1. The voltage across the capacitor leads the voltage across the resistor by 90 degrees. Is it correct? From the phasor diagram, if you master the phasor diagram, you know that the voltage across the capacitor does not, first of all, lacked the current. It lacks the current by 90 degrees. That's what you should know. The voltage across the inductor leads the current by 90 degrees, and the voltage across what? The resistor is in phase. Is in phase with the current. So that is what you should know. As I said, I did this already on a previous video. You people should go and watch it if you are not understanding. I even explain it with the phasor diagram. So let us proceed here first. I will not draw the phasor diagram here. We waste us our time. So as I was saying here, now the first statement is the voltage across the capacitor leads the voltage across the resistor by 90 degrees. Is it correct? Let us come back. The voltage across the capacitor here lacks the current by 90 degrees. It means that the angle between the angle between VC and current is negative 90 degrees. That is the meaning of lack, is behind. Okay, and the voltage across the resistor here is in phase with the current. It means that what? If this is in phase with the current, it means that the angle between them is the same thing, and therefore the VC lacks the current by 90 degrees. Therefore VC will lack who? Therefore VC will also lacks VR by 90 degree, making statement 1 to be wrong, making statement 1 to be wrong. Yeah. Then statement 2, the voltage across the inductor is out of phase with the voltage across the capacitor. The voltage across the inductor is out of phase with the voltage across the capacitor. Let us see. Voltage across the inductor leads the current by 90 degrees. Is okay. And voltage across the capacitor, so it means that if I'm having something like that rapidly, if this is the voltage across the inductor, if this is the current, this is it. And if this is the voltage across across the capacitor, this is the current, that is negative 90, this is it. It's okay, this is 90 degrees, this is negative 90 degree. Now, are you seeing that the phase difference is okay? They are not in phase. The phase difference between the inductor and the capacitor is 180 degrees. 90 minus 90 will be 180 degrees. Therefore, they are not in phase, making statement 2 to be wrong. Now, let us go to statement 3. The voltage across the inductor leads the current by 90 degrees. This is it. Voltage across leads the current by 90 degrees, making statement 3 to be correct. Okay. Now, let us move to the next question. Okay. The speed of 5 molecules of an ideal gas in meter per second are, so we are having 11, 12, 15, and 18. So the first statement, which of the statements is or are true about the speed of the molecules? The first statement is saying that the root mean square of the molecules is 13.6. Okay, let us go and verify. Very easy to verify. They're asking for the root mean square speed. So it means that what? I will take each speed, I will square it. I will square each speed like this. Then I will divide by 5 to calculate the mean. Then I will take the square root. While doing this, you see that your answer will be 13.84 meter per, I think something like that, 13.84 meter per second. Okay. So statement 1, first of all, is already wrong because it's not equal to 13.6. Now let us move to statement 2. The average speed is less than the root mean speed. Average speed, very easy. The average speed here is simply equals to 11 plus 12 plus 12 plus 15 plus 18 divided by 5. That is average speed. I sum and divide by the total number of speeds. Now you see that while calculating the average speed here, you come out with 13.6, making, they say the average speed is less than the root mean speed. Look at 13.6 is less than 13.84, making the statement to be correct. Now 1 to 3. The most probable speed of the molecule is 12. The most probable speed of the molecule is 12 meters per second. Very correct. For us to know the most probable speed, we look on our set of speeds, which one mostly appears. It is what? It is 12 that mostly appears. Therefore, the most probable speed is who? Is 12 meters per second. Yeah, it appears 2 times. The other one appears 1 time. Therefore, the answer should be 12 meters per second, making statement 3 to be correct. I think when statement 2 and 3 are correct, I think it's B. I don't know. You should verify. Now, let us move to the next question. Let us move. This one is, I think it's quite easy, but many students don't really know it. But it's quite easy. They are asking us, Kirchhoff's first law is based on which of the following conservation law? Okay, you first of all know, Kirchhoff first is talking about what? Kirchhoff current law. He's saying current entering a junction. Current entering a junction should be equal to current leaving the junction. So if this is I, this is I1, I2. So he's saying that the current entering the junction should be equal to the current leaving the junction. So that is it. And that one is which law? When you see law of conservation of energy, law of conservation of mass, law of conservation of charge, from there you can directly see that 3 is correct. Law of conservation of charges, because what? Current is equal to what? The flow of charges. Means that the total number of charges entering the junction should be equal to the total number of charges leaving the junction. Is okay. That is from what? Law of conservation of charges. Since current now is charge divided by time, therefore the current, from the law of conservation of charges, we can directly say that current is also conserved. It means that the current entry should be equal to the current going out. Okay. Now let us move to the next challenging question. Now the next challenging question here, 16. When washing tomatoes in water of density, we are having the density of water already. given to be 1000 is inside the formula bullet, kilogram per meter cube. It is found that a particular fruit floats such that only 15% of its volume is above the water. The density of the fruit in kilogram per meter is. Now, the first thing you should know here is the principle of Archimedes principle is okay. For anybody to float on water, you should know that the weight for anybody to float on water, the weight of the water displaced by the body, the weight of water displaced by the body should be equal to the weight of the body. So that is the condition for anybody to float on water. Should be equal to weight of the body. So from this Archimedes principle, another weight is mass times gravity. Another mass is what? From density equals to mass all over volume. You see that mass is simply equals to density times volume. So mass is density times volume gravity. It means that the weight of water displaced will be equal to what? The density of water, the volume displaced, yes, the volume displaced, the volume of water displaced, then the gravity should be equal to, now weight of the body should be equal to the density of the body. Density of the body, we are talking here, the body is the fruit. Density of the fruit times volume of the fruit times gravity. Gravity can cancel. Okay. Am I having a... Okay. Now, I know that 15% of the tomato is inside the water. It's 15% which is submerged in water. It's not all. It's okay. It means that for us to have, let me see, a particular fruit floats such that only 15% of its volume is above, it's 15% of the body is above. How many percent will be below? 85% is below. Are we understanding? 85% is inside the water. It means that the volume of water displaced here should be 85% of the total volume of the fruit. Okay. Now, from here we will calculate 85% the same as 0.85 V. Is okay. Then we'll come and replace here. It means that we'll have density of water times 0.85. This volume of the fruit times equals to density of the fruit times volume of the fruit. This one cancels. Therefore, the density of the fruit is simply equal to 0.85 density of water. So, by numerical application, we will have 1000 times 0.85. Okay, making the answer to be C, kilogram per meter cube. Okay, so that is it, student. So nothing to fear, very easy. Now let us move to the next question. So the next question is a capacitor of capacitance. So you're having the capacitance, which is 120 microfarad, is charged by a 9-volt battery through a resistor. The resistor is 80 kilo ohms. The time taken for the capacitor to charge to acquire 75% of its final charge in seconds is. So please, student, you should first of all understand what are we doing here. We are charging a capacitor, so we should first of all come up with the equation of charging a capacitor. So the voltage across the capacitor for charging is simply equal to the initial voltage of the battery into 1 minus exponential of negative t all over r RC. This is the equation of charging a capacitor. I think you people know it. Now, but here, I'm not interested on the voltage across the capacitor. I'm interested on the what? On the charge across the capacitor. So from C equals to Q on V, this implies Q is simply equal to CV. So for me to come out with an equation in terms of Q, I will multiply all this one by what? By C. So I'll have CVT equals to CV0 1 minus exponential of negative t all over R all over RC. Now CVT is who? Is QT equals to Q0 into 1 minus exponential of negative t all over R RC. As simple as that. So this is the charge across the capacitor at any time t. Now, what am I looking for? I'm looking for t when the charge across the capacitor t is 75, acquires 75% of the initial charge. So this implies 75%, at least 75% is 0.75 Q0 should be equal to Q0 1 minus exponential of negative t on RC. So I'm looking for that t when this value takes 75% of Q0. So I will replace this to find the t. So this cancel here. Then I'll apply ln on both sides to remove the exponential. I will have 1 minus, pardon, this cancel here, this implies I will have 0.75 equals to 1 minus exponential of negative t all over RC. Is okay. So this implies 0 minus 75 equals to 1 minus exponential of negative t all over RC. I'm looking for t. I think an opposite student should make t here the subject. I'll bring this one here. I'll bring 0.75 minus 1. I'll have negative what? Negative 0.225 equals to negative exponential of negative t all over R. Negative cancel with negative. So my t negative, I will apply ln. I'll have negative t all over RC simply equals to ln of 0.25. So t is simply equals to negative RC ln 0.25. So that is the value of t. Okay, after the numerical application, we obtain t will be 13.3 seconds, making the correct proposal to be C. Now let us move to the next question. A diffracting grating with line 60 line per millimeters. You should know that n here represent the n here is the number of line per millimeter, so 60 lines per millimeter, yeah. Then is illuminated normally by a monochromatic light of wavelength. We're having the wavelength 600 nanometers. The number of fringes seen excluding the central fringe. So I really explained this here on my previous video, so you people should go and watch it if you're not understanding. Okay. Now the first thing to do here, I think I always advise you to change these lines per millimeter to lines per meter. And I told you that to change from line per millimeter to line per meter, it depends. When I want to change from millimeters to meters, I should multiply by what? I should multiply the millimeter times 10 to the negative 3. So I will come here. Then since the millimeter is down, you see that the times 10 to the negative will go up. It's okay. Since I'm having lines all over millimeters like this, I will come multiply by 10 to the negative 3 will go up as line times 10 to the 3 per meter. Is okay. So anytime you want to convert from line per millimeter to line per meter, you multiply by 10 to the 3. Okay. So here I will have lines per meter. So that is it. Now, what are they asking for? They are asking for the number of fringes seen, excluding the central fringe. Number of fringes seen. A fringe is a bright region, as I explained in my previous video. A fringe is a bright region. I want the number of fringes formed. To find the number of fringes, I first of all find the order of diffraction, which is n. I should first of all find the order of diffraction. How can I find the order of diffraction? For us to find the order of diffraction here, I should first of all find for us to find the order of diffraction here, I will use the the formula of diffracting grating. It's okay. I will use the formula of diffracting grating, which says d sine theta n is equals to n lambda, where n is the order of diffraction. Okay. Now, for me to have the number of order, I should go at the maximum. Is okay. So I should find the maximum order. So at maximum order, for me to find the total number of order, I should find the maximum order. At maximum order, another what? Sine theta n is simply equals to 1. It means that d is simply equals to n lambda. Now another d is what? D is 1 all over n. is equals to ND. So this implies N maximum is simply equals to what? 1 all over ND. As simple as that. Pardon, here is lambda. Here is lambda. Yes. 1 all over N lambda. So my N maximum is simply equals to 1 all over N is what? N is 60 times 10 to the how many? 60 times 10 to the 3 times lambda, which is this lambda, 600 times 10 to the nano is times 10 to the negative 9. So 1 over 600 times 10 to the 3, there is number of line per meter, times 600 times 10 to the negative 9 to change nanometer to meter. Okay, now I'll have my answer here is 2.77 something like that. Now, as I always say, when you people having the order, don't take the decimal. We only deal with what? With the whole number. It means that my maximum order possible here is how many? Is 2. Is okay. And if it is 2, it means that there are how many fringes? Remember, when I'm having 2 maximum number, it means that we should have this there's 1, 2, 3, 4 to the left and to the right. It means that if the maximum is 2, it means that the fringes, the bright regions to the, let's say to the left is 1, 2, and to the right is 1, 2. Are we together? To the right, pardon, this is the right. To the right is 1, 2, and to the left is 1, 2, making a total of 4. Without counting what? The central, without counting N0 is okay. So I'll have here N. This N1, N2, this N negative 1, N negative 2. So how many fringes are there? 1, 2, 3, 4. And the maximum order is what? 2. So therefore the answer is what? 4 fringes. So that is the number of fringes. Okay, now let us move to the next question, making the correct answer to be D. Let us move to the next question. The next challenging question we are having, in the circuit shown in figure 4, the voltmeter reads, we are having the value that the voltmeter is reading 2.4 when 2.4 volts when the switch is open and 2.1 volt when the switch is closed. Given that the internal resistance of the DC source is 2 ohms. Okay, now this one is quite easy. Let me draw the diagram and we do it. I think this is current electricity. This one is V here. This is a switch. Okay, we are having E here. We are R. Okay. Now, what you should know here is that there's a small internal resistance that it did not show it. Let me show it because a battery is having an internal resistance small R here. Okay. Now, when the switch is open, I want you to understand that what when the switch is open, this resistance is not part of our circuit. I can remove it. It's okay. It means that the voltmeter is measuring what? It's measuring the EMF of the battery. It's okay. When no current is flowing, the EMF is measuring the EA. When S is open, this S open, the voltage there is the EMF of the battery, which is given as 2.4 volts. So be careful. Understand. It's like when you're in practical, you're taking your multimeter, you're measuring the voltage across the battery. You're measuring the EMF of the battery. It's okay. You're measuring the EMF of the battery. Now, when S is closed, you see that what? When I close this, R now is part of our circuit. It means that current now is flowing. It means that the voltage that I'm measuring here is okay. It's no more the EMF. The voltage I'm measuring here, it is the same as the voltage I'm measuring here because they're in parallel. It's already part of our circuit. It means that if I'm measuring the voltage here, since this is in parallel with this, is the same thing. Therefore, the voltage here V is simply because the voltage across R. This is what we call the external PD. External PD. Okay. Now, they are asking us to find out the value of R. I know that what from the formula EMF, you predict current electricity, EMF is equal to the internal PD IR times plus the external PD, which is VR. Is okay, which is TI times, in fact, we will do it. So this is it. EMF is internal PD, which is I small r, plus, exactly, because, as I said, the battery is not perfect. It's okay. The battery is not perfect. It means that the current that the battery is delivering to this R, or the voltage that is delivering to this R, is not all coming here. Some is being what? Some is being lost by who? This internal resistance. This is it. It means that the EMF that the battery is delivering, one part of it is taken from him again because it's not perfect, and the other part is taken from the external resistance, making the external paging. Now from here, are you having the EMF? Yes, the EMF is 2.4 equals to IR. Are you having V? VR, yes, VR now, I think VR is 2.1. They mentioned it there, 2.1 volts. So from here, I think I can find the current flowing the circuit is simply 2.4 minus 2.1 divided by the internal resistance. Now, they gave the internal resistance. Let us verify. Yeah, the internal resistance is 2. So, making the current in the circuit to be 2.4 minus 2.1 divided by 2. So the current flowing in the circuit is 0.15 amperes. But we are not looking for the current. We are looking for who? The external resistance. So from V external, which is IR, so R is simply equals to who? V external, which is 2.1, divided by the current flowing in the circuit, which is 0.15, making the resistance to be 14. Making the resistance to be 14 ohms, and the best proposal or the correct proposal to be C. As simple as that. So you should master really the difference between EMF and the external PD when the switch is closed and when the switch is all open. Let us move to the next question. Next question, we are having the thermodynamic process if the heat supply is dQ and the change in the internal energy is du. The quantity of heat supplied to the energy to the system is given by. So we are having a curve like this. Let me draw it fast. So we are having V1, V2, P1, P0, P. So it is a pressure against volume. Now we all know that what the internal, the energy supplied to a system, the change in the energy supplied to a system dQ is equal to the change in the internal energy of the system plus the change in who? The work done by the work done on the system. So that is it. So from there, literally for the correct proposal, where there is not W. Okay. Now I also know that. Let me come up with the expression of W in terms of, because I'm seeing the area. Okay. Let us see how we can derive so that area can come out. So another work done normally is force times distance, and force is what? Pressure. Pressure is force all over area. Are we together? Okay, it means that force here is simply equals to P, a pressure times area. Okay, if I come and replace it here, I will see that work done is simply equals to what? Pressure times area times D, making it to be pressure times volume. So if I differentiate now W, I will have pressure times dV at constant what? A constant pressure. It means that I can replace this formula by du plus plus P d dV. Now you see that this one, the dimension of this one is the dimension of area. Look at, is the dimension of area under this graph, because area is this distance and this distance, so it is PV. So I can simply replace this by area, making the correct proposal to be A. As simple as that. Now next question.